So here's our agenda. We plan to start just at 3 o'clock, which we just hit. As we have people trickling in, I just want to give one more second. To give I have 3 presentations here on modeling and modeling adjacent topics. But I'm hoping to get as many. Maybe we'll do the first presentation and then do our camera. So because of the amount of people entering late. So I think we'll do that. So if you want to turn off your cameras for now you know where the button is. And we'll start with our first modeling session, and we will take our photo in between the first and second speakers. Our first speaker is Jiafu Mao of Oak Ridge National Lab. And I have a pre-recorded presentation, and he is in the chat room, ready to take your questions in real time as soon as I figure out how to share the right app.
Hello, everybody. I'm going to present one of our recent work on the development of observation-based global multi-layer soil moisture products for 1970 to 2016. I would appreciate the excellent contribution from my co-authors, especially Dr. Yaoping Wang from the University of Tennessee at Knoxville, and the funding support mainly from the DOE Rubisco project. So, as you all know, the majority of soil moisture products fall into 5 categories: in situ measurements, satellite observations, offline land surface models, reanalysis, and Earth system model simulations. For the in situ measurements, they provide the most direct soil moisture observations at the pond scale, but are too sparse to be interpolated to the global level. Then for the satellite-derived soil moisture records, they only penetrate the top few centimeters of soil and contain errors and spatial gaps typically caused by factors such as a change in path, dense vegetation, frozen soil, water bodies, and radio frequency interference. So the soil moisture in land surface model, reanalysis, and Earth system model simulation, those model the results. They usually span multiple soil layers and have no spatial or temporal gaps, which is convenient for regional and global analysis. However, model simulation may contain considerable errors because of inadequacies in the model physics, parameterization, and drivers. So theoretically, merging multiple source datasets would overcome the limitation of individual datasets, resulting in long-term global gap-free multi-layer soil moisture products for the research purposes. Therefore, the need exists to develop global merged soil moisture products that comprehensively combine the information from the latest in situ and satellite observation, offline land surface models, reanalysis, and Earth system models using advanced fusion methods. Here we mainly used the unweighted averaging, optimal linear combination, and emergent constraint. Several new monthly multi-layer soil moisture datasets at global half-degree resolution for the 1971 to 2016 were produced for this study by implementing these merging algorithms onto different combinations of the mentioned raw soil moisture estimates. Then, the merged soil moisture products were evaluated against the reserved 40% in situ observations, as well as a few graded reanalysis, satellite, and machine learning upscaled soil moisture datasets. Although the merging process aimed to use as many existing soil moisture datasets as possible, The graded datasets in this table were not used in the merging because of incompatible vertical resolution, non-global spatial coverage, or short temporal coverage. Such evaluation against multi-source graded datasets complements the evaluation against in situ observations by providing sanity checks on the behavior of the merged products at large scales. Then this is the evaluation, one of the evaluation results. For the evaluation against the validation set of the ISMN soil moisture observations, the merged products generally showed smaller magnitude of bias, smaller RMSE, and higher correlation than the surface dataset, than the source datasets from which the products were merged. The bias of both the source and merged datasets shifted from mostly positive to mostly negative from the shallowest to the deepest soil layer, indicating a tendency toward the overestimation of vertical soil moisture gradient. The shallower soil moisture layer also tended to have lower RMSE and higher correlation than the deeper soil layers, and the bias values of individual merged products were generally similar. Then the evaluating results for the merged soil moisture products against independent or semi-independent graded soil moisture datasets were highly dependent on the evaluation dataset. The asterisks here indicate that the magnitude of the bias RMSE or correlation of the merged product is better than the product's source datasets in the same column. So within each column of each panel of this dataset, this figure, the merged products generally had lower RMSE and higher correlation than the average RMSE and the correlation of corresponding source datasets. And these offline reanalysis satellite-based products, the ORS-based products, they generally had lower MSE and higher correlation than the CIMIC 5 or CIMIC 6 model-based products. Because all the merging procedures essentially involve averaging over multiple source datasets, the variability and the trends of the merged product may be damped compared with the source datasets because of mutual cancellation. So to examine whether this is the case, power spectral densities were calculated on regionally averaged time series of the merged products and the source datasets. The power spectral densities of the mean, ORS, OLCORS, and ECORS, which are the offline reanalysis satellite products applied used different constraining methods. For those products, they very rarely exceeded the boundaries of the source dataset, showing that, at least at a regional level, these merged products did not underestimate the temporal variability in soil moisture. We also examined if those soil moisture products can reproduce historical drought events. So for the evaluation against selected drought events, in these figures, low values in SC-PDSI and soil moisture anomalies are indicative of drier condition, and higher values indicate wetter condition. So for this United States drought between 1985 and 1992, the SC-PDSI showed gradual expansion of drought from 1985 to 1988, and a gradual alleviation from 1989 to 1992, with the most severe drought being reached in the northern Great Plains in 1988. So similar erosion patterns can be also seen for different 0 to 10 centimeter soil moisture anomalies from different merged products. These figures show the annual partial correlations of soil moisture with precipitation, left, temperature, middle, and shortwave radiation on the right, and the spatial distributions of the dominant driving factors for individual merged soil moisture products, which is displayed on the rightmost figures. Based on partial correlation, precipitation was the dominant control of soil moisture variability in different products over most of the globe, and they generally had significant positive partial correlations. In all the merged products, all air temperature had significant negative partial correlations with soil moisture in many continents, especially southwestern United States, eastern South America, Southern Africa, and the Mediterranean. The primarily negative correlations were consistent with the physical expectation that higher temperature induce higher evaporative demand and thus lower soil moisture. However, downwelling shortwave radiation was rarely shown to be a dominant control of soil moisture variability for different merged products. Just a summary of this study. So for this study, we achieved the goal of creating long-term gap-free multi-layer soil moisture products for the 1970 to 2016 period at global half-degree monthly temporal resolution for 4 different soil layers. And this dataset now can be downloaded at this link. So overall, the merged soil moisture products showed better performances than their source datasets, temporal homogeneity, the ability to capture large-scale drought events, and the regional climatic response characteristics across the globe and multi-layer soil layers. The ranges of performance metrics of the new datasets against in-situ measurements and semi-independent graded soil moisture estimates were broadly within the estimates reported by previous soil moisture evaluations, although making a strict comparison is difficult because of the widely different spatial temporal coverages and resolutions. 3 new soil moisture products, which are those often land surface models, reanalysis, satellite products, those combination of those products constrained by different constraining methods. So those products were shown to perform better than those based on those SIMI5 or SIMI6 model results. Therefore, they are recommended for future applications, such as the detection and attribution of historical changes of soil moisture and associated extreme events, providing the initial and the boundary conditions for atmospheric models, benchmarking various types of models, and managing drought and flood risks. Thank you.
Thank you, Jiafu. And do we have questions? I see one here from Yulong. What merged methodology is used? Scale match method or machine learning or something else? If you want to turn on your, there you go.
Yeah, good question. So here, so as mentioned, so we use 3 different methods. So the first one just the mean of different products. The second one is optimal least combination method, which essentially considers the weight of different products compared to observations. The third was the emergent constraint method. That's a kind of method you can use the relationship between, for example, between the soil moisture and their driving factors or climatic driving factors, and use those observed temperature precipitation to constrain these soil moisture results. So unfortunately, we didn't, for this work, we didn't use the machine learning method. So we would like to, apply it next step, especially when we try this kind of high resolution upscaling results for some at the regional scale. Thank you.
Any other questions? Yulong says thank you. If not, we'll move on. We're going to do our group photo now. So how we do a group photo is if everyone can turn on their screens, and I will put you onto my big screen capture ability here. and I will just take screenshots and tell you that I'm taking your screenshot. And then I'll cut and paste your photos into some group shot later. But I'm just basically waiting for a good collection of faces. Let me see how many we got. We have.
Do we smile or shake our head at you, or?
You can, I will let you express your individual personalities. You can pretend someone just asked you the square root of 965. If you want, that's always fun. We have about 70% participation. So let's everybody make your desired expression. And there's one here. That was a false alarm on that one. There's number 2.
I like the pussycat who's part of the picture.
Always fine. Whoops, that's not it.
Tell us who you completed so that we don't have to keep smiling for an hour.
Oh, hey, you got to be happy all day. I have taken everybody's photo, so thank you for participating. We are good there. Bring down, and we'll move into our next presentation by Yulong Shah, who I have a recorded presentation, and Yulong is in the chat because he asked a question before. And I will start this as well.
Today, my talk is a validation for NLDAS and GFS soil moisture and application to National Soil Moisture Network and the US Drought Monitor. First, I want to acknowledge my colleagues Helen Wei, Mike Ballard, and Daryl List. This slide gives you an outline. The outline includes introduction for NLDAS, GLDAS, and GFS, station observations and satellite retrievals, validation for model soil moisture, application model soil moisture product to US Drought Monitor and the National Soil Moisture Network, and finally give you a summary. This slide shows the NSAP EMC NLDAS website. NLDAS run 4 land surface models: NOVA land surface model, Mosaic land surface model, Sacramento model, and the Wake model. All 4 models produce soil moisture for different soil layers. The details, please see EMC NLDAS Drought Monitor and the NASA NLDAS website. This slide introduces the NSAP GFS V16 GLDAS system. The GLDAS run NOVA land surface model in weakly coupled mode. GLDAS uses updated land dataset for the vegetation type and soil type. Use the GDAS atmospheric forcing and gauge-based CPC daily product. The GLDAS using GDAS initial for daily run. The spatial resolution is 13 km and for global domain. The GLDAS provides operational GFS land initial conditions, including liquid and frozen soil moisture, as well as soil temperature. This slide gives you a summary of model product. NLDAS include 4 land surface models and run the land model uncoupled for NLDAS domain, include corners, South Canada, and North Mexico. In 1H degree resolution, the period cover from 1979 to present. The GFS V15 run NOVA model in coupled mode. Global domain 13 kilometer resolution. The data period cover from the June 2015 to March 2021. And the GLDAS GFS v16 run NOVA model for 3 days offline. Use the GDAS forcing and the CPC global daily gauge-based precipitation. Global domain, 13 kilometer resolution. The data period cover from June 2019 to present. This slide shows station observations and satellite retrievals. This shows national soil moisture work. And this is the international soil moisture network. And this two part is include all the in situ measurement from the national and global stations. This is satellite data, include SMOPS and ESA-CCI. Besides the blended soil moisture, they also include separate satellite retrievals, such as SMAPS, SMOS, ASCAT, and AMSR, and Central. This slide shows validation for GFS with observations. Top panel shows 10 centimeter soil moisture validation, and the bottom shows 10 to 40 centimeter soil moisture validation. The red line is observations. Blue line is GFS v15. Green line is GLDAS GFS v16. If we compare the time series for the different stations and models, the result shows the GFS model can generally capture the observed daily variability, but not magnitude. GFS v16 has a lower soil moisture than the GFS v15. The two GFS results are much more similar to each other than to the ops. The QA/QC is needed for real-time station measurement for some station pre-array. This slide shows validation against NLDAS, SMOPS, and ESA-CCI for Green Plain. The top panel shows NLDAS validation. The black line is GFS v15. Blue line is GFS v16. And the green line is mosaic. Red line is NOVA, and the orange line is weak. The results shows GFS soil moisture is comparable with NLDAS, although NLDAS weak is whiter. The right panel shows the SMOPS, include SMAP, SMOS, near real-time SMAP, and near real-time SMOPS. The result shows SMOPS, SMAP, and SMOS is helpful for model validation, but near real-time SMAP and SMOS is limited for validation purpose due to a lack of QA/QC procedure and many missing values. On the bottom left shows the validation against the ESA-CCI. The ESA-CCI combined is green. Orange is ESA-CCI passive. Red is NLDAS NOVA. Blue is GLDAS GFS v16. Black is GFS v15. The results shows the ESA-CCI is useful for GFS soil moisture validation. This slide shows validation against the satellite retrievals, include ESA CCI combined, ESCCI passive, SMAPs for North America, Africa, Asia, South America, Australia, and Europe. The results show GFS soil moisture is drier than satellite retrievals, and GFS V16 is driest. A passive is wettest when compared with others. This slide shows application model soil moisture product. This is an application for US drought monitor. This slide shows application for the monthly CPC drought briefing. This slide shows the NLDAS application for National Soil Moisture Network. This slide shows a summary. GFS soil moisture is compared with NLDAS station measurement and satellite retrievals for the 2019 summer. The results show the GLDAS GFS V16 is drier than the GFS V15, and the satellite retrievals for nearly all regions. Both station measurement and satellite retrieval help for validation model soil moisture. The result shows the model can capture the observed soil moisture daily variability when compared with station observations. However, model cannot capture magnitude well. The NLDAS has been applied in National Soil Moisture Network and Operation US Drought Monitor. Hopefully, GLDAS model-based soil moisture will be used in the International Soil Moisture Network in the future. That's all. Thank you for your attention. If you have any comments and suggestions, please send an email to Daryl. For technical support issues, please send an email to me. Now, I'd like to take your question. Thank you.
Thank you, Yulong. And you're in the chat. Do we have any questions for Yulong? One thought, it's not a question, is that there are a lot of models, and I saw Smurge on there as well. And we see over time that models come and go, and satellite products come and go, and they evolve over time. And there's probably and it's hard to keep track of all the papers that come out in these various, someone develops a model and runs it and compares it to data, and then we lose track of where that product may come from. It may be useful for the NCSMMN group to develop, and it's somewhat there at the nationalsoilmoisture.com, but having a concerted effort to kind of document all in one place, maybe not the data's there, but at least pointing to or illustrating where you can find all of the different data sources. Just getting a table of networks, getting a table of data archives of satellite data would be useful to the community, because I do get emails asking me, hey, I don't even understand. There's so many acronyms to follow. I don't understand everything. Is there a place that all of this information can be held that's actually curated and alive? And that may be something that we want to look at in as a community, developing and this is very important part of it, a curated data set that or website that shows where all the data is and gets checked periodically. I know that the remote sensing products there's an active effort at CIOS to keep track of all the data sets that are being produced purely from a remote sensing platform. It becomes much more difficult when you talk about model products because they're probably more numerous.
Yes, Mike, I wanted to add it, for example, for my work, for my previous, for NLDAS, we just is totally, that work is support the US Drought Monitor and the National Soil Moisture Network. This is a total offline model simulation. But for the GLDOS and the GFS, another part, we want to support the numerical weather forecast. Is for short period, but enhance the forecast scales. But as you know, the soil moisture as an initial condition can affect the model forecast part. This means we only did some preliminary evaluation, but use the in situ and the satellite retrieval to look. Our model is how close to the in situ and the satellite retrievals, and give is a broad picture. Look, our model, similar to the soil moisture, how well, and then help us to improve model simulation and model prediction. This is basic our purpose. Like you know, I talk with you many times. In situ is a very good product, is a referent and is ground truth. Even there is some errors, but this is a measurement error. But for model, we have much more errors for the different part. You know, this means is hard for us. But for how to use this product like a model, and also use the in situ and the satellite retrievals to find the missing part and the error for a model, the parameterization and the model parameters still is a challenge issue. Yeah. Okay, I did it here. Thank you.
Yep. Okay. There are a few comments in the chat if you want to follow up with Tyson and Claire. If we have time, we can revisit them later because some of them are broader questions about modeling. We'll move on next to Stephen, who some of these questions can be carried through in his talk as well. So Stephen, you are going to be sharing your screen, correct?
That's right.
All right. I will be quiet.
All right. Well, this was a great introduction. The previous two talks really fed in quite nicely to what I'm planning to talk about, and also to this goal of utilizing our community of scholars here to achieve some of the higher level goals that would be really great for us as a community to work collaboratively and cooperatively on. So I'm going to end my talk with kind of a call for community action or community collaboration. And I think there's tremendous potential here, tremendous opportunity. I'd first like to thank Mike Kosh for all of his efforts in organizing and running this conference. It's been great to see virtually all of the people online, and it's definitely opened it up to a much larger pool of people than if we would have been in person. So that's wonderful. Today, I'm going to talk about assessing the accuracy of CMIP-6 soil moisture simulations in the contiguous United States. So unlike the last two talks, focus in here on the continental United States. I'd like to thank my co-authors on this paper, Dr. Shanshui Yun, who was previously in my lab here at Ohio State and was back to China, where he is a professor at Hohei University, and the recently appointed or defended Dr. Zach Leeser, who defended his dissertation this month and will be continuing on as a postdoc in my lab. So they're, of course, the ones who did all the work. They're the ones who get all the credit. I just get to talk about something that's kind of exciting. So this month, the Intergovernmental Panel on Climate Change started rolling out the results from the most recent assessment report, and the summary for policymakers was released, and also drafts of all of the chapters. So one of the things that I went to look at right away was, where does soil moisture feature in the IPCC report? And if you go to chapter 11 and look under the weather and climate extreme events in a changing climate, and in particular in section 11.6, they look at both observations. So what are the observed trends in terms of soil moisture under a changing climate? And also, what are the projections in terms of future soil moisture? One quote from that section is that overall, there are contrasting results on the performance of land surface models and climate models in representing soil moisture. And so we saw a little bit of that, I think, in Yulong's presentation, where depending on the region and the season and which data set you're using for validation, performance can vary. And also, there have been relatively few studies, especially global studies, that have used all of the observations that we've spent the last 2 days talking about. So in some small way, our paper was meant to address this, but it's certainly not a comprehensive or complete or the final word on this topic. So the objective of our paper was to evaluate surface soil moisture from 18 CMIP-6 models and compare the historical trends from the CMIP-6 models with CMIP-5, and looking at the NLDAS-2 model and in situ observations. We had 3 questions. What are the regional and continental soil moisture trends that are shown in CMIP-6 over the historical run, which uses the natural and anthropogenic forcings and attempts to provide a solid climatology. So this is from 1850 through 2014. And then to validate or compare or confront the models with observations, as Paul Dermeyer might say. How well do the trends in CMIP-6 agree with NLDAS-2 and with the in situ observations? And then to see how has the state of the science and the state of the art with modeling advanced over time. And so are CMIP-6 models doing a better job than what we saw with CMIP-5? Now, one thing you may have noticed is that we're focusing on 0 to 10 centimeters. And this also came up in one of the questions that was just posted in the chat. And this is an ongoing issue that is a challenge when we're trying to compare, validate, integrate data from multiple sources. In this case, we focus solely on the top 10 centimeters because that is common across all of the models in the CMIP archive. But we would also like to do this for the entire soil column, or the entire, at least, column that's modeled. But every model has a different depth and different depths at the same locations. And so how to unpack and fairly compare and evaluate this was too involved for the scope of this particular paper. So that's one thing I'm throwing out there that needs to be done. Here's a list of the models. I won't go through these in detail. There were 18 from CMIP-6 and 14 from CMIP-5. For the NLDAS-2, we focused particularly on the NOAA land surface model and not all of the NLDAS-2 models. We did to standardize the data sets. We generated standardized anomalies. So for each product, for each location, we use the long-term mean and the long-term standard deviation, and then generated standardized anomalies or z-scores so that we could remove systematic biases or standardize each product individually. We regridded all of the data sets to the 1/8 degree grid that NLDAS-2 uses. One of the questions from the review process was, well, how sensitive are your results? Obviously, going from a GCM resolution to 1/8 of a degree is a big jump. So would this look different if you regridded at 1 degree or 2 degrees? So we replicated our results for those. I'm not going to show those here, but they are qualitatively consistent with the results that we show. And then a subset of data from Zach's doctoral dissertation, and also some of the sites that are available through nationalsoilmoisture.com. We used just 303 stations in the continental United States from the following networks for this assessment. So here's another place where we know there's many more stations, and we would like to use a larger and richer data set. So we can talk about that. So let's hit some results. First, let's look at trends. So the figure A at the top is the 1850 through 2014 results from the CMIP5 ensemble mean, so the average across the 14 models, and the CMIP6 ensemble mean averaged over the continental United States. These are smoothed, and the shading in the background here represents some of the spread, 1 standard deviation around the ensemble mean. So we can see some correspondence between CMIP5 and CMIP6. We can see some interdecadal variability here in moisture conditions, and we can see a fairly strong trend in drying from around 1970 through the 2014 period. However, this multi-model ensemble mean hides a lot of the intermodal variability. So this down here takes the overall trend from the multi-model mean and looks at each of the individual models and says, if we generate this same plot with every single model and calculate the trend, what do those look like? So some of the models show much more substantial drying, some show actually a wetting over the entire time period, and a good number are near the multi-model mean. So here again, first cut analysis, it would be nice to do this for all of the models, but we just focused on the ensemble mean. Then in this final plot, we zoom in to the 1980 through 2014 period and show the interannual now. These are not smooth, interannual soil moisture anomalies from CMIP5, CMIP6, NLDAS, the NOAA model, and the in situ observations. Here, we're just looking at the grid cells that are co-located with the in situ observations. So this is so that we can compare apples to apples, but it doesn't represent the overall continental US. We see some differences in the trends. So the CMIP6 better matches with NLDAS2 and the in situ observations, and CMIP5 deviates. Its trend is a little bit stronger, and some of the interannual variability is not quite matched as well with observations. We can also break this down. So everything on the previous slide was showing one data point per year for the entire continental United States, but there's a fair amount of regional variability. And so here we've broken it out into 7 regions, shown the spatial for each grid cell, the trend in soil moisture at those locations. Very hard to read, but there's a stippling on here. It's the areas that look a little bit darker in color, and those are the ones where there are statistically significant trends over that 1850 to 2014 period. So we see some regions of the continental United States with statistically significant drying and some with wetting. And if we take any particular region and look, there's a spread again amongst the individual models that make up that mean. We can also then compare some of these trends in terms of the observations. And so during the first 2 time periods, we don't have NLDAS2 or in situ observations. So it's just a relative comparison of CMIP5 to CMIP6. Is there a difference in what those models are showing? We're using the same 14 models in this figure right here. So that is a apples to apples comparison. We can see that are differences in what the trend of CMIP6 is versus CMIP5. Also, the variability in CMIP6, as represented by the solid lines right here, is reduced a bit. So that's good. It means that the models are converging in their answer. Once we get to this last 2 time periods, we can now add in other data sets to at least qualitatively or quantitatively compare with. And so when we look at NLDAS2, which is the green dot, and the in situ measurements, which is the black dot, we see that CMIP6 is now moved closer to, but is still statistically significantly different from at least the trend shown in the in situ observations. And so while there has been a reduction in intermodal variability from CMIP 5 to CMIP 6 and a shift in the right direction, that CMIP 6 matches more closely with the observations, there's still a good deal of room for improvement. And so 3 things that we concluded from this study: there are evidence of significant long-term soil moisture trends in regions of the continental United States. But when we aggregate everything together, the wetting and drying tends to cancel out. So we don't have a statistically significant trend over that entire 1850 to 2014 time period. We see less intermodal variability, and we see that CMIP 6 has moved toward the observations, but there's still substantial model uncertainty amongst all of those Earth system models that are comprised. So to conclude, what I want to instigate or encourage or ask is, can our community come together to utilize the knowledge, the expertise, all the great data sets that we've seen presented over the last couple of days to undertake a more detailed and comprehensive analysis of the CMIP 6 models. And here, I'm particularly focusing on this group of models because a lot of the conclusions about future drought frequency and severity come from the GCMs. And a lot of the motivation for action and adaptation and mitigation obviously is focused on this report. Nonetheless, in the drought literature, there's relatively less activity around evaluating, comparing, improving those the soil moisture component of those models. So some thoughts that I had was to break this out for individual models, focus on different geographic areas. Also, the previous 2 talks both had a global focus. Wouldn't that be awesome to have a paper like this that did this globally, looking at some of the sources of bias and what are the physical factors, and then maybe addressing some of those issues with model depths and looking beyond just the surface. So with that, I will conclude and turn the floor back to Mike.
Thanks, Stephen. Do we have questions for Stephen? The chat has a few comments, but they were trickling past.
Hey, yeah, sorry. Go ahead, Mike, if you like. I don't want to cut you off.
No, go ahead.
Okay, Stephen, thanks. Great talk. Can you go back a couple of slides where you have show the trends as a box plot? Yeah, right there. That's really, really interesting. I just wonder, just sort of technical thing here, in the right-hand side where you have the in situ, so the data that's going into the box plot there for the CMIP 5 and 6, are those only for the sort of cells or regions that align with the in situ data, like geographically located with the in situ data?
Correct. So in this case, we've just focused on the grid cells that are overlapping with where the in situ stations are, which is definitely not complete coverage of the US. So that's why this figure I show separate from the other things, the spatial maps or the overall trends where we used all locations. Here we're trying to match as best we can between the in situ observations and the model simulations.
Yeah, good. That makes a lot of sense. And so a totally different question I have. You had a map where you maybe had a map of the trends across CONUS from the CMIP models. I'm just curious if you see spatially any any correlations there or observations about how that map may compare to maps of temperature trends or precipitation trends?
Yes, good question. So precipitation is probably the one that kind of relates to this. So we know over the Midwestern United States, over this time period, we've seen increases in precipitation and precipitation, intense precipitation. We have not done the analysis to say what is the correlation between the model simulated soil moisture and precipitation. There is a good paper by Cook et al. That does have a very comprehensive analysis of drought trends from the CMIP-6 models and precipitation. And there's some differences when you use soil moisture versus precipitation in terms of the frequency, intensity of changes. So they're definitely internally consistent. So the precipitation trends drive the soil moisture, but they don't match exactly.
If there's time for one more question.
Yeah,
Mike,
go ahead. One more question.
Thanks. Have you compared, Stephen, have you looked at how the two models represent the soil moisture, like field capacity and wilting point? And some of my analysis, again, this is more regional analysis looking at NAR. I've noticed that they may not represent, they may not capture the dynamic range I see in the in situ data. Is this something that CMIP 5 and 6 handle better, or are they different between the two? It's just a general question.
Yeah, good question. So in this study, there are 18 different models, each of which has its own land surface scheme and soil parameters and characterization. We skated around looking at the specifics by standardizing for each model using the model's mean and standard deviations. So coming up with standardized anomalies that we're comparing. So I'm sure there are systematic biases as it relates to field capacity and how saturated the soils can get and those kinds of things. We did not delve into that in great detail here.
Thanks.
Quick question from Marina. Why only 300 plus in situ sites, and why those particular ones? Is there a quality control?
Yeah, so this was based on quality control, based on the period of record. So we were trying to get stations that were the longest possible stations so that we could match over that time period. And then some of it was convenient sampling. These were stations that had made it through some of Zach's quality control work for his dissertation. And so again, it's not, there's room, even based on the data that we have in our community today, to do a more comprehensive example of this.
Don't cry, sweet baby.
I'm looking to try. Sorry. Go ahead, Stephen. Sorry.
Yes, so just in response to Marina, this is not all of the stations that we could use. It's just the ones that were most readily available and the best quality for this assessment.
So then just quick, obvious follow on, in addition to the challenge you've given the community, are you all planning to bring in more stations, or what's your next step on this work?
Yeah, this was a side project. So it was something that Shan Shui and I chatted about and wanted to do. He had done a similar assessment for CMIP 5. And so with the upcoming publication of the 6th assessment report, we wanted to at least make it to update that analysis for CMIP 6. It would be great to have a more than just a couple of months of evenings and weekends to kind of put it together. And it would be great to pull together a larger group of people, because as we've just seen in this session, there's been a lot of data that have already been developed, analyzed for a global analysis. And so we could not reinvent the wheel, save some time and effort by pooling our efforts in that way.
And Stephen, I have a question. For example, now you did your work for the past time, even present time. Did you have any thought you wanted to extend your work for the future time? For example, in the future, for example, to look the future trend, is compare the past or the current, and give some sense in future how to handle like for agriculture risk and fire risk and in the future. This any thoughts for that part?
Yeah, I think that's a great idea too, Yulong. I think soil moisture has a lot of value for that purpose, and looking at projections and projected changes would be great. We didn't touch that at all with this project.
Okay, thank you.
All right.
Just a thought. I know you did a past is great. Yeah.
Okay, thank you. And thank you, Stephen. We're going to jump into a 4-minute break right now. Give everybody a chance to stretch their legs. We got 1 more hour. We have our next speaker ready to go. So we want to start pretty quick after 4 p.m. Eastern and give everybody a chance to finish strong. So please stretch your legs a little bit, go get your last sip of water, and see you back in 4 minutes.